残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話にな
Calculus! Okay, everybody, we're back. Today we're talking about section 4.3, what derivatives tell us. So, in section 4.1, we saw that the derivative is a tool for finding critical points, and that critical points are related to the local maximum and minimum of a function. What we're going to show in this section is that derivatives, both the first and the second derivative, tell us a lot more about the behavior of functions. So let's start it off with a definition, a kind of obvious one, increasing and decreasing functions. So suppose a function f is defined on an interval, let's call it I. We say that f is increasing on I if f of x2 is greater than f of x1 whenever x1 and x2 are points in I with x2 bigger than x1. That is, a function f is increasing if it sends bigger stuff to bigger stuff. Bigger inputs give you bigger outputs. Similarly, we'll say that a function is decreasing on the interval I if f of x2 is less than f of x1 whenever x1 and x2 are points in I with x2 greater than x1. So decreasing functions reverse the order, i.e., decreasing functions send bigger inputs to smaller outputs. Okay, fair enough. Is it going up or is it going down? Increasing and decreasing, fair enough. So, the derivative of a function gives us the slopes of the tangent lines of that function's graph. If the derivative is positive on an interval, that tells us that the tangent lines on that interval have positive slopes. That means that the function is increasing on the interval. Think of it like this. If you're on a roller coaster and you're looking straight ahead and you're looking at the sky, it means you're going up. If you're looking at the ground, it means you're going down. The sign of the derivative tells you whether or not the tangent line is positive or negative in its slope. If it's positive, that's like looking at the sky. If it's negative, it's like looking at the ground. It tells you whether you're going up or down. So, a positive derivative on an interval implies positive rates of change on that interval, which in turn indicate that the function is increasing in value. And just in the opposite direction, if the derivative is negative on an interval, the tangent lines on the interval have negative slopes, and the function is decreasing on that interval. That is, as you put in bigger and bigger numbers, you're going to get out smaller and smaller values. And not smaller in absolute value, but just lower on the number line. So, for example, you could put in 1 and get out negative 2, and then put in 2 and get out negative 27. This is still decreasing. You're getting lower stuff on the number line as you put bigger stuff on the number line in. Yeah? So it's not in absolute value. It's just, as you go to the right on the number line, are you going to the right on the output, or are you going to the left? If you want to look at a graph, we can do that. Let's check it out real quick and make sure we got the concept down. Okay, guys, here I've got a graph of a good old-fashioned quadratic, good old-fashioned parabola. As we can see, just looking at this guy, over here, as I go to the right, as I go further in this direction, my function is getting lower and lower in its outputs. So that is, I start high on the left and I'm going down. Imagine this like a track that a ball is rolling down. So I'm decreasing, I'm going down over here, and then when I hit that vertex, then I start increasing after that. Notice what's happening to the tangent line, which I just have playing an animation here. Notice that over in this region, all of the negative x values, my tangent line is pointing down. It's got a negative slope. Like over here, negative slope, it's pointing down. Hit 0, now it's got a positive slope. It's pointing up. So, derivatives quite naturally, just by their sign alone, tell us whether a function is increasing or decreasing. Let's do some more. Okay, so back at it and on to the first theorem. Theorem 8, test for intervals of increase and decrease. So let's suppose that f is a continuous function on some interval I, and differentiable at all of the interior points of I. Remember, we talked about interior points in 4.1. So, if f prime of x is greater than 0 at all of the interior points of the interval I, then f is increasing on the interval I. In the exact same way, if f prime of x is less than 0 for all interior points of I, then f is decreasing on I. So, greater than 0, increasing. Less than 0, decreasing. All right, let's try out an example. Okay, on to it. Example 7. Let's find the intervals on which the following functions are increasing and decreasing. Start it out with the first one. F of x equals x times e to the negative x. So, first step, we're going to take a derivative. This is all about derivatives. Using the product rule, we'll get that f prime of x, and let's write this out. F prime of x, using a little bit of the product rule, we'll get, well, it's going to be the first function's derivative, so x prime times e to the minus x, plus x times the derivative of e to the minus x prime. Okay? Doing this, we're going to get 1 for the derivative of x, so we'll get e to the minus x right there. And then we'll get x times the derivative of e to the minus x, which, using a tiny bit of chain rule, is minus e to the minus x. Okay? Now I can rewrite this as e to the minus x e to the minus x. And if you're good with it, I can do just a little tiny bit of simplification and write this as 1 minus x e to the minus x. Bada bing, same thing we got right down here. So by the product rule, we get that f prime of x is 1 minus x e to the minus x. So first thing we're going to want to do is solve f prime of x equals 0. Solve for when it's 0. We'll talk about why we do this in a moment. So, f prime of x equals 0 when 1 minus x e to the minus x equals 0. Since a product is 0, if and only if one of those things is 0, at least in the real numbers, what we need is either 1 minus x to be 0 or e to the minus x to be 0. So, notice, e to the minus x is never 0. That's a positive number to a power. You can never take a power of a positive number and get 0. So, the sole critical point is x equals 1. That is, when x is 1, 1 minus x is equal to 0. This is the only time when f prime of x is equal to 0. So, If f prime changes sign at all, then it does so at x equals 1 and nowhere else. This tells us that f prime has the same sign throughout each of the intervals -infinity to 1 and 1 to infinity. Okay, let's stop for a second and make sure we get what's going on. The gist of it is that if a function is continuous, which we definitely know that 1 minus x times e to the minus x, that's going to be continuous. Okay, so this guy's continuous. If it's going to change sign, then it has to pass through 0. That is, if you go from being negative to being positive, you have to go through 0 if you don't have any jumps. So when f prime of x is equal to 0, this is the place where the function could potentially change sign. Now notice it doesn't have to change sign. Quick and easy example of that is something like x squared. So here, let me draw a quick tiny sketch of a graph up here just to show you an example. So think of something like x squared. If you take x squared, you know that this guy is a parabola. Bam, it hits 0 and it bounces right off. So it's possible to hit 0 and bounce off. There are two things that can happen. You can go touch 0 for a moment and then bounce right off, or you can go through the x-axis, and that's when you change sign. So what we're going to do next is we're going to check and see if this happens for f prime of x. This will tell us what the sign of the derivative is on each of these intervals. So how can we do it? Well, we can't change sign anywhere except at this place, x equals 1, the point where f prime of x is 0. So just pick any point in the open interval from -infinity up to 1 and the open interval from 1 to infinity. Then evaluate f prime at each of those points and look and see whether they're positive or negative. Look and see whether what you get out is greater than 0 or less than 0. So looking here, between -infinity and 1, let's pick an easy point. How about x equals 0? Yeah, that's in there for sure. So f prime of 0, well, if we go through and we plug it on in, 1 minus 0, e to the minus 0, that's just 1 times 1. So f prime of 0 is 1. That's definitely bigger than 0. And this tells us that f prime, the derivative, is strictly greater than 0 on the interval from -infinity up to 1. This tells us, using the exact same stuff from before, that f is increasing on the interval from -infinity to 1. Now, we try throwing something in from the interval 1 to infinity. We can't use the endpoints to test. They're not in this interval. It's an open interval. So I just choose 2. X equals 2. That's certainly between 1 and infinity. Okay. F prime of 2? Well, we just go through and we plug it on in. 1 minus 2, that's -1. E to the minus 2, well, that's just 1 over e squared. So it's -1 times 1 over e squared. Okay, that is minus e to the minus 2 if you want to think of it that way. And that's definitely less than 0. All right, so f prime is, oops, I think I wrote this backwards there. There we go. F prime is less than 0 on the open interval from 1 to infinity. This means that f is decreasing on that interval for exactly the same reasons we just talked about. So, and this is nice, you can also notice that f has a horizontal tangent line at x equals 1. That's because this is a critical point, yeah? We have a 0 derivative right here. Now, it's not the case that every critical point corresponds to a place where you have a horizontal tangent line, but the critical points where you have a 0 derivative certainly do. So what's going on is we have a tangent line that has positive slope from -infinity up to 1, 0 slope at 1, and negative slope from 1 on off to infinity. There we go. First example down. Let's try out number 2. In number 2, we're going to look at the function f of x equals 2x to the third plus 3x squared plus 1. Scroll down a little bit. There we go. Now we got it right here to look at. So f prime of x, 6x squared plus 6x, just a little bit of classic old power rule. And doing a little bit of factoring, since both these guys got a 6x in them, I can factor that as 6x times x plus 1. Now, we're going to find the intervals of increase and decrease. The first thing we're going to do is solve and set f prime of x equal to 0. Since f prime of x is 6x times the quantity x plus 1, we just set that equal to 0, and we can see pretty easily that this is going to be 0 when x is 0 or x is negative 1. These are the critical points of f of x. So if f prime changes sign, if the derivative changes sign, then it does so at these points and nowhere else. That is, f prime has the same sign throughout each of the 3 intervals, since we're cutting it at 2 places at both of these critical points, at the interval from negative infinity up to negative 1, negative 1 up to 0, and 0 up to infinity. We'll evaluate, just like before, we'll evaluate the derivative at a point in each of these intervals and determine the sign. So, between negative infinity and negative 1, I'm going to choose negative 2. All right, plugging it on in. 6 times negative 2, that's negative 12. Negative 2 plus 1, that's also negative. So we got a negative times a negative, and in fact we have precisely 12, and that's definitely positive. So f prime is greater than 0, and f is definitely increasing on the open interval from negative infinity up to negative 1. Now we're looking for a point between negative 1 and 0. Let's just choose the middle. X equals negative 1/2. So plug in negative 1/2 in there. We'll get 6 times negative 1/2. That'll be a negative number. Negative 1/2 plus 1, that's positive. So negative times positive, negative. All right, and in fact, you get precisely negative 3/2. Definitely negative. So f prime is less than 0, and f is decreasing on the open interval from negative 1 up to 0. Okay, last interval between 0 and infinity. Let's choose x equals 1. Why not? Okay, plugging 1 on in. 6 times 1, it's positive. 1 plus 1, also positive. In fact, you get precisely 12. So that's bigger than 0. F prime is greater than 0. F prime is positive. And we may conclude that f is increasing on the interval from 0 to infinity. Notice from this, just because we did solve and set the derivative equal to 0, we can tell that the graph of f has a horizontal tangent line at both x equals negative 1 and x equals 0. Cool. Couple of examples down. Let's do some more. Okay, now we've got a little bit of a handle of what's generally going on, so it's time to talk about one of the more important results in the section. This is a classic. Theorem 9, the first derivative test. So, suppose that f is a continuous function on an interval that contains a critical point. Let's call it c. And let's also assume that f is differentiable on an interval containing c, except perhaps it's c itself. I know that's slightly confusingly phrased. So f is continuous on an interval that contains c, differentiable on an interval that contains c, except it may not be differentiable at c itself. Okay, so if f prime changes sign from positive to negative as x increases through c, then f has a local maximum at c. So that is, if we're going up and we start going down, that means that at the very top, at the moment where we switch from going up to down, we hit a maximum. So that's telling us when we go from positive, i.e. the slope of a line like this, to negative, i.e. a slope of a line like this, that moment is or corresponds to a local maximum. So that is the place where f will have a local maximum, i.e. f of c will be a local maximum of f. In the reverse direction, if f prime changes sign from negative to positive as x increases through c, or sorry, it should be decreases. Decreases through C, then f has a local minimum at C. So this is the case where you're going down and then you start going up. That moment when you switch, that's a minimum, or at least a local minimum. All right. Finally, if f prime is positive on both sides of C or negative on both sides of C, then f has no local extreme value at C. This is the type of situation where you basically just take a break for a moment at C. This is like x cubed. I'm increasing. I stop, and now I'm increasing again. Increasing, and then I flip it around. So something like this, or conversely, I could be decreasing, stop, and then keep decreasing. So little bends can be misidentified, if you want to think of it that way, by the first derivative test. This is sort of the type of location where the first derivative test alone is not enough to pick up what's going on. So looking at the first, it's enough to pick up what's going on, but just the derivative itself doesn't pick it up with just a critical point. So we have to check these signs. We basically need at least 3 pieces of data. We need a critical point C, and then we need the sign of the derivative on either side of the critical point to gain information about whether or not that critical point corresponds to a local maximum, a local minimum, or neither. Fair enough. Let's move on to an example. Okay, example 8. Let's consider the function f of x equals 3x to the 4th minus 4x to the 3rd minus 6x squared plus 12x plus 1. Oof. A degree 4 polynomial, kind of long. All right, let's find the intervals on which f is increasing and the intervals on which f is decreasing. Then we're going to use this info to find the local extrema of f, extrema. So, first step, find a derivative. Differentiating f, we just use the power rule. We find out that f prime is 12x to the 3rd minus 12x squared minus 12x plus 12. A lot of 12s. Works out nice. So factor out a 12 from everything and do a little bit of algebraic manipulation, a little bit of factoring. You can turn this on into 12 times the quantity x plus 1 times the quantity x minus 1 squared. So if you want to see this real quick, just factor 12 out of everything. You'll have an x cubed right there minus an x squared minus x plus 1. Notice we're just going to do some factoring by grouping. That is, if we pull an x squared out of both of those first terms, I will pick up an x minus 1. And now, if I factor a negative 1 out of this guy and that positive 1 right there, I'll pick up x minus 1. So, using a little bit of factoring by grouping, now we can see that this is the same as 12 times x squared minus 1 times x minus 1. And since we can factor x squared minus 1 as x plus 1 times x minus 1, this turns into x plus 1 times x minus 1 times x minus 1. So that's x minus 1 squared. And bam, we got the same thing again. Cool. Okay, so if we're solving f prime of x equals 0, this will give us the critical points. And looking at our function's derivative right here, x plus 1 is 0 when x is negative 1. And x minus 1 is 0 when x is 1. Okay, so our critical points are x equals minus 1 and x equals 1. The critical points determine where we're cutting up the interval from negative to infinity at. I.e., if we cut it up at 2 places, we'll get 3 chunks. One chunk from negative infinity up to negative 1, the first critical point, the leftmost critical point. One interval from negative 1 up to 1, that's the interval between our 2 critical points. And a third interval from 1 on up to infinity. That's everything after our furthest critical point to the right. These are intervals where f prime doesn't change sign. The only places where f prime can change sign are at the critical points x equals minus 1 and x equals 1. So we'll choose a test point in the interval from negative infinity up to negative 1. Pick whatever you want. Pick negative 2. And we're going to start playing a little fast and loose with these here. Let's pick negative 2. Let's plug it on in. 12, negative 2, plus 1, still negative there. So positive, negative. Take anything and square it. It is going to be, well, since we know we're not plugging in something that makes it 0, it's going to be positive. All right, so positive, negative, positive. It's going to be negative. So f prime is less than 0. And correspondingly, f is, oh my gosh, something went wrong here. Let's fix this. F is decreasing on the interval from negative infinity up to negative 1. Similarly, testing points in negative 1 up to 1, an easy one to test would be 0. Let's throw it in there. 12 times 0 plus 1, that's positive. So positive, positive, something squared, positive. So we're going to find that that's going to give us something bigger than 0. This is going to be, f prime is going to be positive on this interval. Picking something between 1 and infinity, let's try 2. 12 times 2 plus 1, once again, positive, 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 since we're squaring. All right, so we get that f prime is greater than 0 on the interval from negative 1 to 1 and the interval from 1 to infinity. Correspondingly, f is increasing on both of these intervals. So, f is a polynomial. This means that it is continuous on the interval from negative infinity to infinity. It's continuous everywhere because f prime changes signs from negative to positive as x passes through the critical point x equals negative 1. The first derivative test tells us that f has a local maximum or minimum value at negative 1. Plug it on in, we'll get f of negative 1 is minus 10. Okay, so we can also notice that f prime is positive on both sides of the critical point x equals 1. So f does not have a local extreme value at x equals 1. Okay, let's step back quick. This feels like a lot of stuff at once. Let's look at a graph of f and see exactly what's going on. Okay, I have a graph of our function right here in blue. So this is that big long polynomial there. And even bigger, I've graphed out the derivative with a little bit of a slider on there. I mean the tangent line with a little slider on there so I can move it on around. Let's look at what we got. So here's our function. What we saw in the problem is that at negative 1, the function had a local minimum. And then at 1, the function had neither a maximum nor a minimum. Okay, neither a local max nor a local min. This is absolutely correct. That's the lowest point. That's the bottom of a valley right down here. And up over here, we just take a little tiny break for a minute. We're not increasing or decreasing at 1. And this is just because if we slide our tangent line on over, we can see that we got, let's see. Oh, got to turn my tangent line on there. Okay, we got negative slopes, negative slopes, negative slopes. Oh, we hit 0 down in here. And then we go positive, 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 positive. Oh, stop. Get a 0 slope right there. Now, as we keep going, it's back to positive again. So if I just put that slider on play, you can see that it's just bouncing right around there. And hey, at 1, we have neither a local max nor a local min. We do have a local min at -1, and in fact, that does turn out to be a global minimum, an absolute minimum over all of the real numbers. But for all intents and purposes, we're just thinking about it as a local minimum right now. After all, a global minimum, certainly also a local minimum. So we've been talking a lot today about local extrema, but what about absolute extrema? It seems like this is almost entirely missed by what we're doing. What's going on? Well, the answer is as simple as you might hope. Namely, just think about it like this. You can have a lot of local extrema on an interval I, but you can only have one absolute maximum or absolute minimum. Now, the absolute maximum or minimum can occur at more than one place, but you can only have one. You have one. If you have a bunch of different ones and they're not the same, then one of the numbers is bigger than the other, and it means the other ones are not absolute maxima. Or conversely, one of them is smaller than the others, and one of the numbers is not an absolute minimum. So maxima and minima of the absolute variety are unique. And because of this, we can actually determine absolute maxima and minima using facts about local maxima and minima and uniqueness, provided we restrict our interval properly. So let's suppose that f is continuous on an interval I that contains exactly one local extremum at a point C. If you have a local maximum at C, then f of C is the absolute max of f on the interval I. Similarly, if you have a local minimum at C, then f of C is the absolute minimum of f on I. So this only applies to situations where you have an interval I with exactly one local extrema at a point C. Okay, now, is this really useful? It kind of feels like it's not. It turns out that actually, yeah, this is pretty much enough. So, suppose you have, some interval I and you have more than one local extrema. Let's draw a quick picture to get a sense of how we can use this to actually fully resolve the problem. Okay, so you got a little XY axis here. Let's just finish drawing some little arrows on that, make it look all nice. Or maybe it even looks worse now, I don't know. But there we go, okay. So let's sketch ourselves a interval and a little function. So let's take a to b. Let's make this our interval I. Okay, and I'm gonna really mark that here. There we go. And this is I. The interval I is this guy right here. Okay, so maybe we've got some kind of a function. I'm gonna sketch a quick graph here. It doesn't really matter. I'm just gonna do one for the purposes of this example. Okay, there's my function. There's the graph y equals f of x for some function f. Let's jump back to some other colors really quick. I'm going to trace on up from b and trace on up from a to the graph of my function. This gives me f of b and f of a. There you go. Something like this, yeah? You get f of a and f of b. Okay, now we can pretty easily see that neither of the endpoints correspond to maxima or minima. However, on the other hand, we can certainly see that we do have an absolute max and an absolute min on this interval. One right here and one right there. Now, if my drawing was perfect, which it certainly is not, you would be able to very clearly see that the derivative should be 0 here. is a little bit wigglier than intended, but basically the tangent line through here is 0. Yeah, tangent line through there is 0. So these are critical points, but I've got 2 of them in the interval. How do I deal with this? How can I figure out what's going on? Well, pretty straightforward. I'm just going to take this whole interval and I'm going to slice it in half. I'm just going to go cut it into I1 and I2. Now, on each of these subintervals, I can apply theorem 10. So I know that I only have one critical point in each of these subintervals, and they must correspond to absolute maxima and absolute minima. One of the two. Each of them must correspond to one of the two. So we go through, we test, and we see what's happening. This one we'd look and we'd see, okay, we've got a local maxima here. We'd apply the first derivative test, something like that. Look down here, local minimum, apply the first derivative test again. Using this theorem, I go, oh, okay, this point right here, this guy corresponds to an absolute maximum of f on the interval I1. Over here, this guy corresponds to an absolute minimum of f on I2. Now, just looking at the outputs that I get when I plug in this point and this point, i.e. looking over here, I can figure out that this is the absolute maximum of f on the entire interval I, and that this guy is the absolute minimum of f on the entire interval I. So this is a little bit of a theme just throughout what we do in mathematics. If we can do it for one thing, and we can cut up the cases where there's more than one thing into simpler cases where there's only one thing, then we've really dealt with all the cases. So we can deal with situations where there's more than one critical point or more than one local extrema in an interval just by breaking an interval up into smaller ones where there's only one. Okay. So let's try to make use of theorem 10 and see if we can do an example. Okay, example 9. Let's verify that the function f of x equals x to the x has an absolute extreme value on its domain. So, this is one of those functions that teachers love to throw at people. It's a tricky one. Let's make sure we got the derivative down. So the thing to notice, if you recall, is that e to the x and the natural log of x are inverse functions. So we could write, if we wanted to, that x is equal to e to the natural log of x. Okay, that's definitely true. E to the natural log of x is x. Fair enough. All right. Now I can see that x to the x is e to the natural log of x, that whole thing to the x. And since taking e to the natural log to the x is the same as e to the x natural log of x, now I found a way to write x to the x in a more convenient form, i.e. as e to the x natural log of x. So this is my function, f of x, and I can rewrite it as e to the x natural log of x. So if I go through and I take a derivative, f prime of x, I'm just going to apply the chain rule. The outside function is e to the x. The inside function is x natural log of x. So I'll get e to the x natural log of x times the derivative of x natural log of x. So this is a little bit of a product rule situation. Going on through, I just keep that e to the x natural log of x just hanging out, and now I turn x natural log of x, I take a derivative, and it turns into the natural log of x plus x times the derivative of natural log, which is just 1 over x. So this is just, and I'm going to turn this e to the x natural log of x back into x to the x, because that's what it's equal to. And this is x to the x natural log of x plus 1. All right, so I run through this up here as well, in case you want to see it in not my terrible handwriting, but since we can rewrite f of x, which is x to the x, as e to the x natural log of x, we can go on through, use a little bit of chain rule, and get that the derivative of f is x to the x times 1 plus natural log of x. So we're going to notice that f is continuous on its domain, which is 0 to infinity. How do we know that the domain of f is 0 to infinity? Well, we're just going to take that for a given right now. Whenever you see this guy, that's what you should expect. If you start plugging negative numbers into this guy, notice things will very rapidly get extremely messy. And also, we can't plug in 0. 0 to the 0 is not a number. So if we start plugging things in like -2 to the -2nd, you'll get that. And now that will end up being positive, but as we vary things, it jumps between positive and negative extremely fast, and you get some super messy behavior. So domain 0 to infinity. All right, fair enough. Now we want to show that f has a extreme value of the absolute variety in the open interval from 0 to infinity. We've got a derivative. We want to find out when f prime of x is equal to 0 to get the critical points. Okay, fair enough. So, thing to notice here is that, and I'm going to give myself a little tiny bit more room down here. So the thing to notice is that x to the x is non-zero. So the only place, or the only way we can get 0 out of the derivative is if we have 1 plus the natural log of x equal to 0. Okay, so 1 plus the natural log of x equals 0. Let's solve it really quick, make sure we got this algebra down. So 1 plus the natural log of x equals 0. This tells us that the natural log of x is equal to -1. And using the fact that e to the x is the inverse function of the natural log of x, I'll get that x, which is, remember, I'm e'ing both sides out. I'll get that x is equal to e to the -1, which is just a fancy way of writing 1 over e. Okay, so this gives us a single critical point. X is e to the -1. Using our previous theorem, we can deal with this. Since there's no point in the domain at which f prime of x does not exist, and we have a unique critical point, the critical point splits the domain of f into the intervals 0 to e to the -1, 0 to 1 over e, and e to the -1 to infinity. Now we evaluate and find out what the sign of f prime is on each of these intervals. So we could pick, say, something very, very small, let's pick like 0.00001, something like that. A small positive number to a small positive number power is once again positive. 1 plus the natural log of a very small positive number. Natural log, remember, approaches negative infinity as x approaches 0. So this guy will end up being negative on the interval from 0 up to e to the -1. Similarly, if you go over to the right far enough, natural log starts to be positive again, or at least starts to be greater than -1. And then we will get that f prime of x is greater than 0 on the interval from 1 over e up to infinity. By the first derivative test, this is telling us that we're we've got a negative first derivative, and it flips to positive. So that means we're going down, and then we're going up. That is a local minimum. And using our previous theorem, the theorem we just looked at, theorem 10, this tells us that this is an absolute minimum because it's the only local minima or local extrema in the domain from 0 to infinity. Okay, this tells us that the absolute minimum of the function x to the x occurs at the point x equals e to the negative 1, i.e. x is 1 over e. At this point, the value of the function is approximately 0.69. Cool. I think this is kind of a cool one. I don't think that it's relatively obvious just by looking at the function that x to the x has an absolute minimum on its domain. And more so, I think if you just look at it, there is nothing to suggest that it should be 1 over e. That's kind of wild. That's a pretty cool fact. So these are relatively powerful tools, even though they seem kind of obvious. Wow, guys, some pretty fun stuff. We learned about the first derivative test. Tomorrow, we'll learn a little bit about what the second derivative measures. We'll learn about concavity.